Good afternoon, all. It's just after 3. I think we might make a move so everybody can wrap up for the day. My name is Marc Englaro, Chief Product Officer at Taggle. Looking at the participant lists, most of you might know me. If not, welcome. Nice to meet you. Today's webinar will follow on from the general Taggle overview that we did last week, and we'll look a little bit more specifically at the evolution of sewer monitoring, which I think is probably one of the fastest moving areas of our product development at the moment. I'd be very interested in your feedback as we go. I think there's about 17 people on the call today. So I think we might do what we did last week, which is to use the chat window to ask questions. If you can't find the chat window, it's under the 3-dot ellipsis at the end of the menu. So after mute, start video, security, etc. The very right-hand side of your Zoom menu is an option that allows you to get access to chat. And I will periodically stop during the presentation and just check what questions we're getting. And I'll answer those as we go. I am recording today's webinar so that we've got a copy of it. If anybody wants a copy a little bit later, feel free to ask. And if you're up, would like a copy of the slides, I can provide that afterwards as well. So I might start the presentation by talking a little bit about the first of our clients that we started working on the sewer monitoring space with. Mackay Regional Council has been one of our oldest and strongest customers, always looking for new opportunities to use technology to solve problems and improve operations and performance. And one of the challenges that Mackay has as a utility is that it's in some of the wettest parts of Australia. I think it's that chart down the bottom is 1.6 metres of water per year, and a good proportion of that falls only in a short period of time in the year. And so the challenges faced by Mackay are just enormous amounts of water that overwhelms the sewerage network, leading to overflows. And wet weather overflows are unfortunate. They're not as bad as dry weather overflows, because obviously everything's quite a lot more dilute. But the story reflected to me by the council was that there's a lot of money goes into maintenance of the sewer network, both in terms of preventing overflows, relining the network, looking for illegal plumbing connections, looking for leaky manholes, to try to track down or try to prevent wet weather overflow events. Without any data, it can be very difficult to work out what maintenance activities are making a difference, if any, to the impact of sewer overflows. And obviously these events have quite negative impacts on the members of the public. So the council came to us with a request to look at building a sewer networking system, sewer monitoring system, that looked at parts of the sewer network that are not traditionally monitored, or at least not traditionally monitored in a fixed fashion. So by using the same communications network that we're using for the smart meters, we've worked with the council to install sewer sensors or level sensors in the sewer, and then using that same low power communications network to be able to pull the data out of the field, concentrate it on a receiver, bring it back to the cloud, and then process and deliver that data through to application software. The objective of using a low power network is to decrease the overall cost of a fixed monitoring network. And so here's an example of the first generation of the sewer monitoring technology that we put in with Mackay Regional Council. This is a Taggle high-powered radio transmitter attached to 2 float switches, with the objective of being as simple and inexpensive as possible so that as many sewer manholes could be monitored at the same time in a permanent fashion. And the target life of these devices is 5 or 10 years. A good proportion of the cost of installing any sort of sensor network is the cost of labour associated with the installation. So this, the design requirements with this was to make it easy to install, but also give it a very, very long maintenance-free life. So as a first generation device, these work reasonably well, although we did discover that sewer network are quite turbulent environments. Let me describe how this is supposed to work, and then I'll talk a little bit about the limitations. So those float switches operate by, as the fluid level in the manhole rises, the float switch lifts and triggers a switch, either a mercury switch or a little ball bearing oriented switch, that tells you that the float has now inverted and that there's now water at that level. And so in the normal operation on the left-hand side here, we would see that a float switch should be off if the pipe isn't full. By strategically positioning the first float switch, as the sewer pipe reaches capacity and starts to fill the well in the manhole, this first switch will actually activate and send a message to the transmitter that then sends a message back to the cloud software. By installing a second float switch and setting its threshold level at the overflow, this second float will tell us that there is an alarm state. We're now discharging sewage into the public, into the environment, potentially impacting the public, which is ideally something we really want to prevent. The first switch gives us some pre-warning that the second event may be occurring. Now, it doesn't have the resolution of other sorts of level sensing, which I'll show you a little bit later, but it does have that advantage of simplicity. In our very first generation of this, installed a few years ago, one of the things that we learned is that sewer networks, particularly in high rain events, can be quite turbulent environments. And these float switches don't smoothly transition from off to on. What they do is they bounce around, both due to water pressure and waves in the water, but also turbulence in the air. And our very, very first generation of these float switches sent the transmitters flat because they were transmitting every time that there was an event occurring. Taggle works worked on a new generation of transmitter based on that feedback, so that there's some business logic in the transmitter to be able to distinguish between a rise or a fall in the float switch and just the bouncing around of the ball for turbulence. Overall, this is a pretty good mechanism for monitoring sewer levels. But where it becomes a little bit more interesting is when you get to correlate the behavior of the sewer levels with what's going on elsewhere. So this is an example of a relatively low-cost rainfall gauge. It's a very high-quality gauge. This is in the same family as the one that the Bureau of Meteorology uses. And attached to the left-hand side of that is a Taggle transmitter. That unit stands alone. It doesn't require a communications cabinet, doesn't require any additional power supply. That's really just a pole concreted into the ground with a little bit of effort to make sure that the rainfall gauge is leveled. And if we put one of these in each catchment area aligning with the catchments of the sewer, we can now start to correlate rainfall in a catchment, which is indicated in this chart in blue, with the sewer level occurring in that catchment. So what we're looking at here are some rain events, which are indicated as these blue bars here, associated with the sewer level sensors. And this is this two float switch style sensor. When the first switch goes on, we get this first level here. So you can see around about 4 a.m. on the 2nd of April, we received a spike in rain, which then very, very quickly resulted in a full sewer pipe. So that sewer pipe is now at capacity. Then a little bit later, about 9 a.m., there was a concerted effort of rain, not quite such a strong peak, but over a longer period of time. Basically all day it was raining, and the sewer level went from operating normally to full capacity to an overflow state, in which it stayed in overflow state for many hours before returning back to normal and down at the normal level. It's this correlation in time that gives us a pretty clear indication about what's causing the sewer overflow. It's very, very clear that the rain is going into the network and it's causing an overflow almost instantaneously. And you can see that on a high event there, a sustained rain event there, a sustained rain event here. And that's most likely to be either leaky manholes or illegal plumbing, allowing rainwater to go directly into the sewer main. And so the maintenance effort associated with trying to work out where those problems are is to go and do smoke testing. So you drop a smoke bomb in the sewer, and then you can see where the smoke escapes, and there shouldn't be smoke escaping from places like this, which is indicating that potentially this house has got illegal plumbing where its rainfall is going into the sewer instead of out onto the street. Smoke testing is not inexpensive. It also upsets the members of the public when you have to go and tell them that they've got an illegal plumbing problem that they then need to resolve. So it's something you ideally don't want to have to do unless you've got a really good reason for it. But the other cause of sewer overflows is when the water isn't coming directly from rain, but instead it's rising groundwater. So rising groundwater will leak into sewer pipes and fill their capacity in that fashion. But what that would mean on a chart like this is that you wouldn't have this correlation in time quite so quickly. In somewhere like Mackay, if it rains for sustained weeks or months, the groundwater will rise over time, and the sewer overflows that occur over an extended period of time that take a long time to rise and then a long time to fall could far more likely to be associated with groundwater ingress than it would be rainwater inflow. The other advantage of seeing sewer levels on a time series chart like this is that you get to pick up situations that you might not have expected. In one particular situation, we experienced the sewer was overflowing on a fairly periodic cycle, 8 or 9 hours apart, which was then identified as being the result of a tidal inflow where a valve on a sewer outlet wasn't operating correctly, and the estuary water was getting into the sewage lines, into the sewage network, and then effectively just filling the sewage treatment plant with salt water. So seeing that what's happening in the sewer network in real time can provide some real insight into problems you might not have known actually existed. And that's one of the challenges of sewer networks, is they're generally considered dark assets. The network themselves, the pipes themselves, are not typically monitored. So there's very little information about what's going on in the network in any particular time. So in order to make sense of this data that we're generating out of the sewer sensors, Mackay began a project to develop a software product called MiSewer. So MiSewer began as part of the MiWater application suite. So we spoke last week about MiWater as a meter data management system and a field app and a customer portal. But on the network side, on the sewer network side, there was an application specifically associated with sewer monitoring that was developed to take advantage of that data that we just presented. And it looks a little bit like this. So a little bit more with a GIS view of the world. where each of these manholes has sensors attached to them, and has some visibility into what's going on in terms of rain, what sensors are alarming, and being able to see that on a visualization that's sort of mapped GIS oriented. When Taggle acquired the MiWater suite at the beginning of last year, we've put a lot of effort into developing the capability of MiSewer. So now, while it has all of the capabilities of the original version, we've now got a number of new features designed to allow the utility to be able to manage this information in a little bit more structured and controlled fashion. So we've now extended the features to allow the utility to set up alarms on these sewer network points when something is going on that doesn't look right. So these green manholes are in the normal state. The orange ones are in a pipe full state, and the red ones are in a discharge overflow style state. In this window here, we can see on the right-hand side, we've got a series of alarms, and those alarms are appearing not only in the software, but sending text messages to nominated people or emails indicating that there's a problem, and allows some alarm management, some tracking style functionality, similar to what you'd expect if you were doing this in a SCADA system. Now, there's often a question about why wouldn't we be doing this in SCADA? Why do we need another piece of software? And the argument is that it's a little bit more around the organizational structure, that the people who are in the operations room monitoring the network are generally focused on very, very real-time events. They're looking at the state of reservoirs, the state of pumps, the state of the water treatment plant. They're looking at managing the network right now at this minute, 24 hours a day, 7 days a week. Sewer monitoring, this sort of sewer monitoring, is something that is a little bit more analytical. The data makes more sense the longer you look, the more data you have. So analyzing the problems with the sewer network isn't something that you can do in 60 seconds. It might be something you want to build a pattern over time, over days or weeks, or potentially months and years, in order to work out what maintenance activities need to occur. So this is less about real-time emergency management and more about longer-term network planning, on the whole. So I've accidentally flipped through to the next slide. What we've got here is a visualization that actually includes the map view. And you can see that we've now got a GIS style layers view that shows the user the ability to filter what sensors they want to look at, what types of sensors they want to look at, whether they're just interested in the ones that are in an alarm state, or those, but also bring in the layers of the mapping. So whether we want to see the services or the imagery, etc. So I want to talk through a couple of scenarios about what this information provides and how you can use it to make the business work more effectively. Because data is cool, but it's not really valuable until you can do something useful with it. This is a scenario described by, again, Mackay Regional Council a few years ago, where there was an unexpected failure in the pumping station. So you can see MiSewer has here a layer that shows the sewer mains, and this is the pumping station up here in the top right. There was a power failure to that pumping station, and the nature of the particular failure meant that the alarms didn't go off back in the SCADA system. So the event seems to start about 7:30 in the morning. About 30 minutes later, this sewer manhole sensor starts sending an alarm saying the pipe is full. So what's happening is that this wet well is filling up, and it's backing up through this pipe here. And this alarm, this alarm here is starting to show that there's a problem. 40 minutes after that, a manhole further upstream goes into an overflow state. So what that means is we've now got this entire pipe is full and it's starting to discharge at this point here. At which point it's now sending text messages to the operations team saying there's something wrong. You might as well go, you might want to go out and have a look at what's going on, potentially send a cleanup crew, but also try and work out what the root cause of all of this is. The power problem at the pumping station was resolved. That alarm went back to green. That one stayed orange for a little while, and then the entire system went back to all clear. So that sort of operates pretty well as expected. But what it provides is another layer of granularity that your traditional SCADA system doesn't normally provide. So this is we see as an adjacent technology, something that extends the visibility of operating a sewer network. So our first experiences with sewer monitoring were with Mackay, but there are a number of other utilities doing sewer monitoring stuff as well. And I wanted to explore a little bit with you the work that SA Water has been doing. SA Water over the last few years have put quite a bit of money into exploring what technologies might be valuable. They had the benefit of a CEO that was very technology and data friendly. And he provided a budget effectively as an R&D exercise to go and explore what data can tell you without necessarily knowing what the business case was at this stage. This project was about actually developing a business case for what technology could be rolled out further. So SA Water has been investing quite heavily in smart network technology in the Adelaide CBD. They've installed smart meters out at Penneshaw on Kangaroo Island. And smart network meters on the network at Port Lincoln. But what I wanted to touch on and focus on really today was the work that they've been doing in the wastewater, which are these sensors up here. There are two areas that the SA Water project focused on, one of which was at Gawler, which is in the northwest of Adelaide up here, and another one at Stonyfell, which is in the Adelaide Hills. And SA Water put quite a few sensors into the network. They're looking at level sensors, but also sensors that could have a look at velocity, the speed at which wastewater was flowing, looking at gas concentrations and odor, air quality and weather, and differential pressure sensors. And I'll talk a little bit about each of those in just a sec. So SA Water took a different approach to level sensing than Mackay. As a bit of a research exercise, SA Water used these much more granular style sensors. This is an ultrasonic level sensor. It sends a click out. It's quite a disconcerting sound if you've ever heard it. A little bit like the way a bat would do echolocation. It sends a click sound out and listens to the echo of the sewer level at the bottom. And in fact, this sensor is quite clever in that it has echo cancellation built into it so that it knows what it should be listening to and what it shouldn't. So for example, the echo off the concrete apron around the pipe down there doesn't mean anything. So it will ignore that reflection and concentrate on the sewer wastewater level, which is the water you can see in the pipe down there. And that'll provide millimeter level accuracy. On the wall of this sensor, of this manhole pit here, we've actually got two boxes, one of which is the Taggle transmitter device. We've also got a battery pack here to extend the life of this, because this transmitter is actually sending information every 5 minutes, which is a little bit more frequently than we would normally do. Because the utility SA Water wanted to see what the benefit of that extra granularity of data was, even though they thought that was more data than they actually needed. The advantage of monitoring a manhole like that is that, and particularly in Stonyfell, is that when you get a dry weather overflow, the benchmark I'm hearing from multiple utilities is a number around about $25,000 for the cleanup exercise. And too many overflow events, and the EPA in each state starts to get interested, and that can be a pretty expensive and disruptive exercise. The findings from Stonyfell in Adelaide was that sewers don't block straight away. They gradually degrade, tree roots get into the network, wet wipes get tangled in the tree roots, and the performance of the pipe starts to decrease over time. And then that's where the blockage starts to occur. And what they were finding is that for all the manholes that we were monitoring, are monitoring in Adelaide, it would provide 2 to 3 days notice that a overflow was impending, was likely to occur, which is plenty of time for a cleaning crew to get out and clean the pipes, get rid of the tree roots and wash out any gravel or whatever the particular issue is, before the wastewater hits the surface. So they've actually prevented sewer overflows, and their crew can be dispatched with a couple of days worth of notice rather than in an emergency. So I think there's a huge untapped business case available for this sort of monitoring. I'm just going to stop for a moment and have a look at these couple of questions we've got in the chat messages. Michael Thomas is asking if it will be recorded, and yes, we are recording. There are, Michael asked how many sensors there are in Mackay. There's about 120, I think, installed in Mackay. There are a similar number installed in Adelaide, possibly a bit more, 160, something in that order. And then other utilities around Australia are exploring the deployment of these sorts of things as well. Sonia from MRC, who is the owner of the sewer project, let me put my glasses on, is indicating that the intention is to have one sensor set per catchment, and ideally putting them in places where you can see what's going on. Chris Manning has said the sewer sensors ultrasonic data can be SCADA compatible. I don't know if that's a question or not. Yes, the data can go directly into a SCADA system. The data can go anywhere you like. So Taggle's principle on this sort of telemetry, on all of our telemetry, is to, wherever possible, use open standards. So these sensors are all off-the-shelf standard sensors from well-known sensor providers like Pulsar or Siemens or Kenran make the blue switches, Vega. And on the data delivery side, we use a whole wide range of open standards for data delivery. Standards include MQTT and web services. We also support DNP3, which allows us to deliver data directly into a SCADA system. So data can go into whatever systems somebody wants, but also the other way around. We can consume data into MiSewer from systems that don't involve Taggle physical devices. So we can ingest data from the Bureau of Meteorology around weather. We can ingest data from sewer pumping stations that are already monitored by the SCADA system. It's much easier to replicate the data than it is to go and install duplicates of sensors around the place. Michael asked a question about the methodology for deployment. That's actually something I'd probably refer directly to to a few people in the actual utilities. So Sonia at Mackay is probably better positioned to talk to where the sensors should go. But on the whole, I think it's you direct the sensors towards the places where you know you've got problems, but you can't quite work out what's going on. So Adelaide, in Adelaide, SA Water decided to put sensors in Stonyfell where they had regular sewer overflows, and in Gawler where they had regular customer complaints about odor coming from the sewer, which is where I'm about to switch to next. So just before I get to the odor sensors, this is the radar sensor. This comes from a company called Hach, and placed down near the wastewater, it'll actually tell you the velocity of the wastewater as well. So when you're trying to track down whether you've got an aging wastewater problem, which is increasing the odor-causing gases, velocity can be a useful piece of data. It's quite an expensive sensor, so I don't think this is one that will be deployed widely across the network in a fixed network sense. So much more expensive than the blue balls, but can be used to calibrate models. One of the innovative areas I thought that SA Water were exploring was to monitor what's going on with gas concentrations. So they know they've got slow-moving wastewater in the Gawler area, and they know that because there's high concentrations of gas in the sewer. There are corrosion issues with the pipes, and there are customer complaints about it, about the smell of the sewer. So rather than just relying on that sort of observational anecdotal data, SA Water installed about 80 of these Acrulog H2S gas sensors. They come in two models. There's a parts per billion sensor, so a very sensitive sensor that will tell you, will measure levels of concentration that you can smell in the air. So the inlet to this sensor is placed at about the standard nose height, and is constantly monitoring the sampling the air and reporting what the gas concentration in the air is. The other half of the sensors were actually placed sampling the gas in the sewer using a parts per million concentration. And by comparing that data with data from the velocity, data from the sewer levels, and from weather sensors, they're starting to build a bit of a model about what's going on that's causing the odor and where the root cause of that might be. They also supplemented that with installing two different models of a differential pressure sensor. So this, another one is from Acrulog and this one's from Vega. And these sensors monitor the pressure difference between what's in the sewer pipe and what's in the air. So it'll tell you whether the vent stacks are operating the way you would expect, and whether the network is outgassing in inappropriate places. And so we have one other customer who's trying to track down seawater ingress into the wastewater. And so one of the sensors that they're looking to use more of is this electroconductivity sensor. There's a couple of different brands of these. We're still exploring what the best supplier of these are, but basically they work by passing a very small current through two electrodes in the sensor head, determining how the conductivity of the fluid, so basically the solidity of the fluid, and that can give an indication of whether or not we've got seawater getting into the sewer network. And we spoke last week about the stream gauge, which would probably be useful in an open channel, but hasn't, as far as I know, been used in sewer monitoring in Australia just yet. I might just pause there for a moment. I've only got one set of slides left to go. I think everybody can see the chat messages there, not so much questions, but feedback from Sonia and from Chris. So I think I'll let everybody have a look at their own chat window to see those. So one of the practical implications of monitoring sewer networks is that being underground and usually under giant steel lids, they're not necessarily radio-friendly environments. What we're finding, though, is that Taggle's high-power radios work surprisingly well out of the box when installed immediately under the sewer manhole. About 80% of the time, and that number varies a little bit depending on where we are, about 80% of the time that it will work with a standard device installed under the manhole, and the radio message will actually go through the concrete and the earth, not through the metal, and make its way back to a receiver station. However, we are seeing that there are difficult radio environments in some situations where that just won't work. And so we're extending the Taggle transmitter module with an external antenna. And I just wanted to show you photos of a few different variations of how that can happen. Here's one. The installation isn't complete, so it's still a bit ugly looking. So it's a sewer manhole with an external antenna connected to the Taggle module. And what they've done is they've drilled a hole from the concrete path into the sewer manhole, chased that in a channel to the wall, and they've placed this road marker antenna up against the wall. It's called a road marker antenna because it is actually a road marker that has been modified to insert a radio transmitted antenna inside the road marker. And it's actually rated to be put on the road. So you can drive a truck over the top of it and it will still operate perfectly well. And it's quite a low profile, very, very low and very smooth. So it's minimized the opportunity for a trip hazard. And there's two photos here where we've installed those actually in a park. In this case, monitoring water meters. But you can see that what we've done in that case is drilled a hole in the pit lid and threaded the antenna through that. Here's a slightly neater one done in Adelaide, where under these Class D steel lids, they've chased a hole in the asphalt, installed the antenna actually just under the surface of the ground, and then covered it with cold mix. And the radio messages get out through the concrete perfectly well, and that's done that so that there's no trip hazard on this quite narrow walkway just here. So there are plenty of real-world practical solutions to installing low-cost transmitters in the sewer network. And so if you've got an opportunity, you're worried a little bit about that communication, I just wanted to give you the comfort that there are opportunities there. And I'm just going to finish up on a little bit new product development from Taggle. All of these devices that I've been showing so far have been predominantly Taggle's LSTT. This is our most advanced telemetry module at the moment. This has the logic in there to be able to distinguish between a float switch turning on as being actual sewer levels or just turbulence in the air. But this box here is still subject to corrosion attack in the sewer network. The gases, the H2S gas turns to sulfuric acid. This box has some nickel plated nuts on the back, so have not been perfect in sewer installations, particularly in those high corrosive environments. We also showed you one earlier where we had an external battery pack, and that's becoming more and more common implementation. So in Taggle, we're constantly working on the innovation and research and development of our technology. So we've taken all of that use cases and all of that feedback on board, and we're developing a new product just about to release called the Cockatoo. All of our new products are named after parrots, I think because they squawk. And the Cockatoo is the biggest of our parrots. And it has all of the functionality of the Taggle LSTT, but with a slightly new enclosure. It's a cylindrical device, so we've got better waterproofing, so it'll handle permanent immersion in water, an IP68 rated system. Stainless steel connectors everywhere rather than anything that was nickel plated. So this will survive the corrosion that occurs inside of sewers. And this profile allows us to fit in 4 batteries. You don't have to have 4 batteries, but you can have as many as 4 batteries, which will increase the frequency at which you can transmit while maintaining these very, very long lives that we want from fixed sewer monitoring. And so those were concept photos. These are actual photos. These are the first production prototypes. We're likely to have these available shortly after the new financial year, so in the sort of, July, August, September timeframe. Supply has been slightly disrupted by the COVID-19 stuff, but not substantially. And so we expect the LSTT will be superseded by the Cockatoo in the near future, just providing a few extra benefits. So I think, again, I've spoken for a very long time without taking a breath. So I just want to open the floor open to questions. If you asked a question and I missed it in the chat message, would you mind reposting it? Okay, well, there's no questions appearing in the chat. Thank you very much for everyone for coming. I'll be here for a few moments more if you do have any other questions. And if anything comes to you afterwards, feel free to contact me or anybody else that you're in touch with at Taggle, and we'll make sure that we can get this information through to you.